So, good afternoon, everyone. First thing you'll probably notice is I am not our president, Mark Chang. I have to let everybody know he sends his apologies. He is testifying before the Budget Committee in the Senate, and that meeting got delayed, and so he has been delayed. He was supposed to be back this afternoon and cannot make it, so he sends his regrets, and I know he's going to be watching the recording afterwards. But today is my distinct honor to introduce the Westwood speaker for today. I should say I'm Lucy Flesch, I'm Dean of the College of Science, and today our speaker is Professor Libai Huang, who is a physical chemist really focusing in on quantum optics. She is very much celebrated for the work she's done. She's a Kavli Fellow of the Kavli Foundation of the National Academies of Sciences. She's a career award winner, and she's the PI on QPID, which is the Quantum Photonics and Integrated Design Center, which is a $14 million investment in the university from the Department of Energy. And so it is my pleasure to introduce Professor Huang, and she's going to talk to us from light to matter, controlling excitations for quantum information.
Thank you, Lucy, and thank you very much for the kind introduction. And the invitation to be here today is a great honor. I want to tell you a bit about what we have been doing both in the QPID Center as well as in my group in general, like how we control this quantum particle called excitons, and in particular for quantum applications. And so I probably be preaching to the choir here, and I think I am. Why there's a need for quantum technology? And this is a famous quote from Richard Feynman, and he said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical." And so he was the one who proposed this idea of quantum computer, in particular, how to utilize the kind of like the power of quantum mechanics to solve very complex questions. And so what are the type of complex questions that we currently do not have answer to, right? And that is not possible to find a solution with our current classical computation technology. And one of those examples is, like, for example, if you want to calculate protein structure exactly, an average protein has 6,000 atoms. And then currently, for classical computer, we cannot predict any molecular structure larger than hydrogen molecule accurately, 100% accurately, right? So there's a very large gap between 2 atoms and 6,000 atoms. There are also problems that come from interaction between many particles, and this, for example, like the interaction between many electrons can lead to superconductivity, and this is also a property that is not possible to calculate with a classical computer. And so this is kind of like what in Feynman's quote of like why the nature is quantum mechanical, not classical, is that this interaction of this quantum particle really matters, and hence, like, to solve the complex problem in chemistry, physics, and materials, we'll need a quantum computer. And one more thing I want to mention also is that the encoding of information is also very important, and in particular, like, for example, like secure information, like banking information, it has been predicted that if we have quantum computers now, like powerful quantum computer, all the banking information can be hacked in a matter of seconds or minutes. So you certainly don't want to be in that position, and you want to have information encoding scheme that is much more resistant to these algorithms. And so, like, where is this quantum advantage coming from? And I just want to give using the qubit as an example to explain this. And so, as we all know, that in the classical bit, you would have a 0 and 1. And so this is like your classical transistor, for example. You can have current flowing through versus current not flowing through, and this would be your 0 and 1 state. And so like for describe a bit, you just need one number, right? So classical bits scale as n. But for quantum bits or qubit, it actually you can have, because of this property that coming from quantum mechanics like superposition, you would have this qubit can be in a superposition of 0 and 1 state. So if you would describe a single qubit, you actually need two numbers. One is describing the probability in the 0 state, and the other is probability in 1 state. And if you go to like 2 qubits, you would have 4 combinations, so you need 4 numbers, and so on and so forth. And so like, the qubits actually scale as 2 to the n, and we all know like the power exponential, right? Like by the time you get to like 2 to 300, you would have a number like larger than total number of atoms in the universe. So this is the power of quantum computing. It's like by utilizing these quantum states that you would be able to compute or simulate or encode information in a much more complex way. And so quantum particles, many quantum particles, as long as you can generate like things like a superposition between different states and control them, then they can be function as qubit. And then many have been proposed or made to qubit, including things like photons, which I would talk in extent today, or electrons, or superconducting circuits, or ion or spin atoms, and exciton, which I would also talk about today, and etc. So, and that, again, like this is, again, based on the audience, I feel like this slide might not be necessary. But anyhow, so what is unique about this quantum particle is that the key thing about that, you need to control them to make them into qubit is to let two aspects. One is this energy quantization, and two is the wave-particle duality. So the quantum effect becomes much more prominent as the size of the particle shrink. And this is because if you go back to like undergraduate, quantum mechanics is like in the this particle in a box example, like if you shrink the size of box smaller and smaller, then essentially what the solution to the Schrodinger equation tells you that the energy of this particle can only take certain allowed values, right? So this would be only these energy levels are allowed. And this is very different than like our day-to-day life of like a classical particle where you feel like all the energy levels are allowed. Like you walk up a stair, you feel like, it's not like any place you cannot step on. And that's because the scale of this energy quantization is tiny. So for a large classical particle, like those quantization feels very negligible. So it just feels like a continuous flow. But for a quantum particle like electron, those steps are actually relatively large for this very small particle. So for the electron, you will see like this discrete energy level. So like these energy levels, and it can be like electronic energy states, or it can be spin or other type of quantum state. It can be function as your 0 and 1 state, right? So this is where those from. And the other thing as a consequence of quantum mechanics is that the solution also tells you that there are distinct wave functions associated with this energy state, so that, is this the particle, you can actually not know exactly where they are at. You only know the probability of where you can find them. And this is this property called wave-particle duality. So like, all this energy level would have associated wave function. And this is where you would be able to do superposition. Like this is why the quantum particle can occupy two states simultaneously. And that's the ability to make these quantum bits. So, I have a animation here just to kind of drive home some of this concept. And again, this audience might not need it, but I didn't know like how broad I need to make this talk to. But first of all, like if you think about like the particle kind of behavior, this is a double slit experiment. If you throw a bunch of particles through this slit, you're gonna see it's like a random pattern at your back screen. But if you go have waves, if you like water wave go through like two slits, and what you're gonna see is that these waves would interfere, right? Because like they can pass through this slit at the same time and they interfere, and they form this interference pattern in the back slit. So now if you throw a bunch of quantum particle at the slit, even though at a single particle, in the end, you will get only a dot at the back screen. But if you throw many, many particles, remember that because where you find these particles are described by the wave function, in the end, they would form this interference pattern at the end. So this is sort of like the quantum essential for like this wave particle duality that allow us to do this quantum operation. So, and today, like these two type of quantum particle that I would be focusing on are the photons and the excitons, and of course, a photon is the quantum particle light. And excitons are the other quantum particle that I would like to introduce now, which is that if you have a very small semiconductors, very tiny piece of semiconductor, and they are nanometer scale. So essentially, what you can do is that you can generate this excited electron-hole pair. So you excite electrons from the valence band to the conduction band, and you left with the what is known as the hole, which is the positive charge behind and the valence band. And because they are strongly confined, right, they have a tiny little nanoscale box to be residing on, then you're going to have this particle that is coming from the binding of the electron and the hole. So the electron and hole are stick together. And so this is known as the excitons. And excitons are very interesting to us because they can strongly couple to light. And so that you can have the conversion between the electronic degrees of freedom and photonic degrees of freedom using exciton, right? And this is why we are interested in these two specific quantum particles types. And so you might say, well, for photon, I know what a photon is. It's a quantum particle light. I see them everywhere, like, like the sunlight is filled with photon, a light bulb is filled with photon. Why couldn't I just use those photons for quantum computation or quantum information? And the reason if you cannot do that is because what we call like a classical light source, like a light bulb, is that you would have these photons coming out at unpredictable time, that's one. And two is that they come out at different colors, like there are many different range of wavelengths, and then also they come out different times, so at different phase. So like these photons are gonna be in some ways that you, if you think about them, they are uncontrollable, like they are not really an unpredictable, controllable way. So we call them classical light because in order to do this quantum application, you need to be able to prepare this photon in a certain state and manipulate them, right? So that is the requirement. And so that's why you can't use light bulb to do quantum computing. And the way that you would need to do is to convert this classical light into a quantum light. And how do you do that? It's like this exciton is the way to do it. That's kind of what I'm going to discuss with today. And the difference between this classical light, for the quantum light, what you need is that they need to be indistinguishable. So like all the photon comes out, they have to be exactly the same in energy and frequency. And they also have to have phase coherence. And that's so, and this is, again, so like how would you then get from like this, the end goal is this quantum lights, like, right? So they are coming out exactly where you know it and in a controllable way and in a defined state. How do you convert from something like classical like light bulb to something like a quantum light? And the way to do it is because you can do that because you can Sorry, this animation will take a second to where I want it to be. So like when you're going to convert this between these two is that you can use this exciton as the medium to convert them. And the reason is that once you confine this exciton in a nanoparticle or a quantum dot, you're going to get to like this particle in a box situation where you have well-defined states. There are two states. We can approximate them as a two-level system. So when the photon is being absorbed, the exciton would go from one state to the other, and this energy level is exactly set. So that when it generates light, they're exactly the same, right? So this is kind of how do you go from the classical light to quantum light limits, and this is at the heart, like the interaction between light and matter, like in this case exciton, is at the heart of quantum photonics. So quantum photonics explores this interface. And the reason is that why that is very powerful is that you need, in a quantum network, like when you do quantum computing or quantum information, you actually need more than one type of qubits. And photon as a qubit is particularly good at communication because photon can propagate very fast, and they also don't decohere very fast because they don't interact very strongly with each other. So photon is very good at communication. But you also need other types of qubits, and these are generally made from materials, and they call matter qubits, or and that in this case it can be exciton. And what excitons needs are to be to interact with each other. So like if you want to generate this complex quantum state that requires many qubits, you would need this matter qubit to be able to interact with each other. So these are kind of things that in quantum photonics that we can use the photon and exciton for. Like we can have these nodes that are made out of excitons, and we can embed them in a photonic structure so that the photon can go between the excitons and interact with them and entangle them. And this is how you'll be able to get to this many body entangled state that will be important for like quantum computing or information application. And so like for us, this exciton material of choice, I'm going to talk about two today. And one is this tiny semiconductor particle called quantum dots. And they are just exactly can be described, almost exactly can be described as a particle in a box model that I looked at before, and you can have these defined energy levels. And the really cool thing about them is that you can make them at different size, and they will emit at different color, because this is just what quantum mechanics tells you, right? So if you put them in a smaller particle box, it will become a high energy, so that's blue. And then if you put them in a slightly bigger box, this will be red. And all these particles are on a nanometer scale. And in fact, like these particles are very good at emitting light. They're so good at emitting light that you can buy now at Best Buy a quantum dot TV. Actually, they are probably one of the more popular TV types nowadays. And the reason they replace many other type of TVs because they have very narrow emission line, so they can make sharper images. So anyway, so because of this kind of property, like they interact strongly with light, they can also be a very good quantum emitter. So this is what we discussing. And the other type of excitons materials that I'm going to discuss are these two-dimensional sheets of semiconductors. And they are exactly what, a few atoms thin, so like atomically thin. And so now your electrons and holes are going to be confined in this two dimension. And the beautiful thing about this material is that you can play them like a Lego. Like you can put them on top of each other, you can twist them, and it's become a very controllable way to control these exciton quantum particles. And so at this new DOE Energy Frontier Research Center that Lucy just mentioned, we call Quantum Photonic Integrated Design Center, is to explore this light-matter interaction at the interface between these emitters and photons. And it's led by Purdue, and it has 8 partner institutions. And the goal of the center is to explore this kind of interface, and in particular, to co-design this interface, like the emitter, like including the extonic emitters, as well as the photonic environment, to realize large many-body entanglement. And this is still currently a large challenge in the field, is because for all the wonderful things I told you about these solid-state emitter like quantum dot, is that inherently, when you make this quantum dot, one is slightly different from the other. And if your angle, like our angle for this photonic state is that we need to make them indistinguishable, that means that we have to overcome like how they are slightly different once you make many of them. And the center is by attacking this big problem by co-designing the photon together with the emitter. So the end goal is to realize all these different type of entanglement between photons, including, starting from single photon to pair of entangled photon, as well as to large clusters and superradiant states. Okay, and this is the wonderful people that are in the center, and many of them are at Purdue. And so with the rest of the talk, I'm gonna kind of zoom in a little bit more to start to my individual lab on like how do we actually understand like this interaction between exciton and photons. And one of the ways that as we learn physics, right, mechanics, if we learn like mechanics, classical or quantum, is that about how the particle moves, tell you everything about the particle. Right? So that's kind of what I do in my lab, is to try to really understand the motion of these very tiny particles like excitons. And the way that we do it is by taking a movie using femtosecond lasers, because these excitons, they have very fast lifetime, they don't live forever, and they can also move pretty fast. And the way that you would be able to capture a motion of something very fast, like light, is by using femtosecond lasers as shutters. I'm gonna play that movie just one more time. Oops. So normally you cannot see light propagate through a cocoa bottle, because light travel at speed of light 3 times 10 to the 8 meters per second. So this whole thing will be over by about picosecond or something. And the way that you would be able to do this movie is by using this femtosecond laser, which is coming out bursts, and each of the bursts is only 10 to minus 15 seconds. And you take a frame by frame, and you kind of slow this whole thing by 1 billion times. This is how you can image light. And so now, what we do in my lab is using similar kind of principle, so using ultrafast laser, femtosecond lasers, to image the light-generated exciton. So like after you use photon to generate exciton, and what happened to those excitons, right? So looking at this light-matter interaction. So instead of just one single laser beam that is showing in that Coca-Cola bottle movie, we're gonna have 2 laser beams. And one is the light that generates the exciton, and second is kind of like as the shutter to track where those excitons have gone through. And it's very important to understand like how these excitons becomes decoherent, like because like the coherence, meaning that they are in phase, like in step, is very important. So like one critical thing we also do is looking at temperature dependence, because one key factor in looking at decoherence, and this is the reason why currently all quantum computers are in cryogenic temperature, is because you need to freeze out all those dephasing and decoherent mechanism. So we also can do this measurement in a cryostat that as low as 2 Kelvin. And so now what we can do is that we can take a movie of how these excitons, after they generate light, how they move in space and in time, and we would have femtosecond time resolution and nanoscale spatial resolution. And in particular, we are interested in how when light generates exciton, how they interact with each other, because this is kind of the key to realize this many-body entanglement, right? Because the exciton have to interact, and the photon convert between the exciton and photon is what allow you to generate these many-body entangled states. Okay, so the first model system that I'm gonna share and is gonna be these excitons in these 2D LIGO sheets that I discussed. Like these are two-dimensional single layer semiconductors, and in particular this case is a layer of tungsten disulfide and tungsten diselenide. And if you layer two different materials on top of each other, in this case two lattices, they have slightly different lattice constant. What you're gonna generate is a new superlattice. So the green dots are where these new superlattices are. And that what it does is that it creates a way of generating an array of excitons, because at this green circle, the structure is slightly different. This is like hexagonal pattern is right on top of each other. And if you're away from the green dot, they're slightly offset. And this leads to the interaction between the two layers leads to different energy landscape for the excitons. And in this case, you can now imagine that the exciton would be located in certain area of this lattice, and you can control that interaction by either twisting the lattice slightly different or using different materials. So this will give you a platform of looking at many excitons in an organized array. And so in this case, this is some simulation that we did in the past with our collaborator. So if we twist these two layers, this is tungsten disulfide and tungsten diselenide, and if we have 0-degree twist between them, the excitons would reside at these known locations, and they would have a relatively high barrier between them. And this barrier is about 100 MeV. But if we change the twist angle to 60 degree, they would go on different location on the lattice, and also they would have a shallower barrier. So now we have this array of excitons, like these are the exciton quantum particle. They're sitting in a control location that we have, and we can now tune how they talk to each other. And so the way that they can interact with each other, for example, they have this dipolar interaction because they both have a permanent dipole because the electron reside in one layer and the hole reside in a different layer. So this will allow them to talk to each other or interact with each other. And this is a platform that is very useful in thinking about this many-body interaction, like how this when the many electron or many exciton interact, what kind of new material property you can obtain, or what kind of information you get. And for example, like as I have already alluded to, like superconductivity come from many-body interaction, right? So like you can have totally different materials behavior depends on how the electron interact in the lattice. So I just want to delve into that many-body interaction slightly more. And the one thing that we argue for is that if we can control this interaction between these excitons, we can use them as like a quantum simulation of materials properties. And that in particular, one of these sort of well-known many-body model is this Haber model, which, and in this case, these excitons are boson, meaning that the combined electron and hole, they have zero charge, is called a Bose-Haber model. And I should also put in a note that in the classical computer, it's hard to solve this many-body question, because when you start to have many particles interacting with each other, then it's sort of exponentially hard for a computer to solve. And the simulation is one of the ways that people have been trying to solve in this problem. So we're gonna first to see if we can realize this sort of Bose-Haber model using these excitons. And in particular, we can tune about the magnitude of interaction of excitons. Like so, here I just simplify the lattice into the excitons trapped in certain wells, and that they can tunnel to a different well through quantum tunneling. And they can also interact with each other. For example, if I put two excitons in the same well, they will repel each other. So in this Bose-Haber model, what it would predict is that you would have different phases of matter. So like in the case of thinking about electron conductivity, it will be entirely different. So if I have the interaction is much stronger than the tunneling, the particle will form this non-conducting state. It's like a crystallized state. And so this electron would not move at all. And if I got into the opposite regime, like the tunneling is larger than the interaction, then we'll have this quantum particle freely moving. It's like, then it will be called a superfluid state. So from a material perspective, if you can design this interaction, you can realize different type of material, like a metallic versus like a insulator, for example. So the other thing that is very critical is that this kind of phases arise purely from the quantum nature of this particle, because if you have a classical particle, first of all, you wouldn't be able to tunnel through the barrier, and that you won't, like, it would not matter how high your barrier is. It would always just stuck in the well, right? So it doesn't form these different phases because of interaction. So anyway, so this is our materials, and we can realize this the understanding of this model by looking at different parameters. So I would just say that we can look at the light that the exciton emitting. Remember, like, one way to look at this exciton is via interaction with photon. So now we're going to look at the light that is emitting from the exciton. So if let's all single exciton in a well, we have an emission at like 1.4 electron volts. But if we put 2 excitons in the well, then this exciton have to actually occupy a higher energy state, about 40 MeV higher. And this is also, again, is also quantum mechanical. So meaning that there's only this allowed energy state, like they can occupy. And if you put in additional particle, they would have go to a different state, because, right, again, this is coming from the quantum effect. And so we also can determine the tunneling factor by measuring the motion of the exciton when they are very dilute. And so we know that now that the U is much larger than J, so that we're gonna see it's a crystallization, or like a insulator state. And there's another interaction that which is this dipolar interaction I alluded earlier, which also plays some role in this system. So now we can use our tool, like taking movie of these excitons, right? So initially, like in early time, we can see this a big blob, which has to do with our laser beam. And this is how we generate the exciton. And you can see initially the center is bright, because our laser beam, the center is the highest intensity. But then if you go to like 200 picosecond, and 500 picosecond and so on later, you can see the center actually becomes dim. And then, and you kind of have like this ripple effects coming out. And what happens there? So if I would just take a cross-section of that image, this is what I see. Initially, it looks like a Gaussian because my laser beam is a Gaussian. But at later time, it actually becomes like a square. And the reason it becomes a square is because if you would think about filling this exciton like a Chinese checker, I don't know if you like to play. It's a very fun game if you have not played before. But Chinese checkers have these holes on it, right? So the reason that you form this square is that if you imagine a Chinese checkerboard, initially you pile all these marbles on top of each other, and then you let it spread out, find this space, assuming like they want to find the most stable space is in this hole. Then if you look at the surface of the Chinese checkerboard, it will be flat, right? Because exactly each hole would have one marble in it. And it's sort of like that, and I guess the quantum analog of that is because this interaction between the exciton leads to that what you want is this insulating state, because the exciton repel each other, so they cannot really move, and they crystallize, and they form these packets like a Chinese checkerboard. And we can kind of look at the long-time behavior when they form this Chinese checkerboard. And what's very interesting is that this first line here, it basically gets down to up here, is when they start to form this square top. And this graph, you can interpret as like the slope of it is the speed of the exciton. So once it forms this square top, the slope here becomes close to 0. So the exciton cannot move at all. So basically we can hold, like we keep adding this exciton onto the Chinese checkerboard. At some point, we have all the motion totally stop. And that has coming from the interaction between these quantum particles. And why it freeze, it has to be that the excitons are still coherent with each other. So the reason they can freeze is because the phase of the exciton are still in lock. If they're not locked anymore, then they will no longer form this Chinese checkerboard pattern. And really the surprising thing is that the time scale that this frozen phase lasts, and it's about 18 nanoseconds. Of course, a nanosecond is 10 to minus 9 seconds. And to many of us, that's a very short time. But for an exciton, it's a very long time because it's an excited electronic state. And so 18 nanoseconds is a large fraction of this exciton lifetime. And what it says is that these excitons are coherent over this 18 nanosecond time, which would allow you to do quantum simulation in this kind of time scale. And what can you do beyond this is that, and this is just a kind of a summary of like what this phase transition happens as like you form this crystalline exciton state. But what can you do beyond this though? And this is like, our paper just came out last week, and this is a perspective written by one of our reviewers on Nature Materials. What you can do about this is that now you can start to control the interaction between this exciton quantum particle. You can actually add other types of quantum particle, or you can change the type of materials. And what you can do is that you can, for example, like I can have mix of this exciton and electrons, and there are theory prediction that you would be able to get to superconductivity. Like you can simulate like what condition like your electron conductivity would be maximized, or like your resistivity will become 0. And this would be realizing a new way of generating materials, right? So anyway, this is kind of like the potential of that. And I'm almost done. I just want to kind of share just one other example of like how we control this tiny quantum particle called excitons in the quantum dots, because I have also introduced them as a different platform of controlling this quantum particle and for different, perhaps, photonics or other applications. And as I already kind of alluded to, like these tiny quantum dots are amazing because they are very good light emitting materials that like make into your TV. And the other thing is that you can actually also form an array of these excitons array by organizing this quantum dot in a perfect line, right? So if you can generate a one-dimensional, two-dimensional, or three-dimensional lattice of this quantum dot, then you can also look at how they interact with each other. And the interesting thing is that if we would think about these exciton lattices again, if they are perfect, they're exactly the same, we'll imagine the exciton wave function and can be delocalized, or like they will be everywhere on this lattice, right? Because if every of this particle is exactly the same, it goes back to this one-dimensional particle in a box model, and you would have this wave function extend over the entire system. And that's like the perfect limits. And in fact, for people who work on things like semiconductor or other, said that is the limit where you calculate your band structure, right? Your band structure assume that everything is perfect and you can have your electron wave function as a block wave, and it delocalizes everywhere. But in the case of like an exciton lattice, and in the case of like solid state material like quantum dots, that each of these quantum dots might be slightly different from each other. And then the question is then how much of this wave-like property, like this quantum property, can we still harness in the system? And because if you start to have things that are slightly different from each other, what you're going to have is that you're going to have interference from waves of a different wavelength. So if you have start to have interference of different wavelength, then they become more localized. So the question is like, how do we maximize the interaction of these quantum dots to harness their wave-like property? And of course, you also have to overcome things like phonons or vibration in the solid state. But anyhow, so that's other things of we are thinking about is how do we get this, make an array of these particles and get these quantum dots to talk to each other. And this is where chemistry comes in really handy. So chemistry can make this particle different sizes. They can also make this particle with different molecule on the surface, so they can be, the distance between these quantum dots will be different. So this is a different way of generating an array of exciton, right? In the previous one, I showed you that you can twist 2 layers to generate this exciton array. Here, I said you can use chemistry tools to organize this particle however you want. And in fact, I think that is a promise of chemistry for quantum in many ways. It's like, molecules or quantum dot, and with chemistry tools, you can be much more deterministic in that approach. So, and scaling up. So like using chemistry tools, then we can make different sizes of these quantum dots so that this interaction term would determine by size, as well as the distance between them. So we now can control those parameters. And in this case, what we really want is so this J is the similar term as the tunneling term that I showed you before. In this case, we actually want this J to be as large as possible because we want these exciton waves to propagate as far as possible. So, so that's a different limit of thinking about this interaction. So now then we can make this superlattice of these quantum dots. And then what we can do is then we can image, as I described also earlier, like how these exciton propagate as function of time and space. And now we're going to look at different temperature because we're going to see how this wave-like property of exciton can survive. And so this is just a one-dimensional slice of like what I showed you before, the distribution of the exciton and as function of temperature. So let's start from like the very low temperature, 7 Kelvin. And again, the slope of this slide tells us how fast this exciton can move. So at 7 Kelvin, this exciton can propagate very, very fast. And but then at some point, like about a nanosecond later, everything stopped. But if I go up temperature, initially the initial part slows down, but then the later part actually keeps moving. And if I go to the highest temperature, at room temperature, it just becomes like slower than like this middle temperature. So it's a very intriguing thing that happened is that the exciton speed is, or in the total propagation is the fastest at an intermediate temperature, like not the lowest temperature, not the highest temperature. And this is kind of actually a very interesting thing because what we really want to understand is like, does this exciton, which is a quantum particle, which have wave and particle-like behavior, do they move as a wave or do they move as a particle? And the answer is they move as both because they are both wave and particle. And what is really cool is at low temperature, what we see is essentially the exciton first propagate very, very fast because the exciton waves can be over many, many quantum dots. But then if that wave hits a defect, and for some of you probably know what's known as Anderson localization, is like if that's a defect, the waves from different sides and have different, slightly different wavelength, they will interfere. The interfere itself of different frequency of wave would localize the wave packet. So at very low temperature, what we see is like the wave-like property of exciton really prevail. So that you see this very fast wave-like propagation as well as localization due to interference. At high temperature, because the fluctuation and the phonons localize the wave of exciton to a single particle, so everything is particle-like. You just have exciton just move like from one to the other, just like a jumping from one to the other. But what's very interesting is in the middle, there is a maximum regime for its transport, and it has to do with both of the wave-like and particle-like transport working together, in that you still have some wave-like transport, but there's some particle-like transport allow you to overcome the Anderson localization by jumping to the next one. So this is a case of like both the wave and particle-like behaviors are important for the transport. And anyway, so I would like to save some time for Q&A, and I just want to kind of leave with this thought of like this interaction between light and matter allow us to really looking at this quantum photonic platform to generate many body type entanglement, and in particular using exciton and control that interaction is a very fruitful way of thinking about how you can generate different materials behaviors, including things like quantum simulation is also a possibility. So with that, I want to thank you for your attention and be happy to talk.
Open it up for questions. Yes.
Yeah, very nice talk. Do you go to page 26? I have a question about that. You said you linked to superconductivity. I didn't quite follow that. Why this relationship with 26?
This is 26.
Yeah. How to correlate that to superconductivity?
Yeah. So superconductivity comes from when you have, like for example, parallel charges, right? And this can be coming from like interaction with phonon, for example. This is one of the leading theory. But there have been predictions made in this particular system, like in this exciton array in 2D materials, that you can have interaction between excitons and charges. Like you can dope this lattice, which Yihang actually is an expert. Yihang is a new faculty member in physics, and Yihang is an expert in this. And in that, depending on the interaction, right? You can. The beautiful thing about this twist moray type of system is that you can control the interaction to allow for different phases of matter. And in this particular heterobilayer, no one have experimentally realized superconductivity yet, but in the twist homobilayer, like some of Yihang's work actually have shown superconductivity. But in this case, like is the interaction between the exciton and the charges would lead to superconductivity.
But this really low temperature superconductivity, right? Really low temperature.
Yeah, of course, it's low temperature.
How about like a high temperature, like oxide, yttrium, strontium, that type? Super high temperature one. Is there any relationship with that?
Yeah, I think that it's again, it would depending on some of these parameters. Like for example, like your U and your J, and those kind of parameter space, as well as like. I mean, in this case, I think like you also have to consider the role of phonons. I don't think in this particular type of TMD system, high temperature superconductivity has been realized. It's all very low temperature, and mostly has to do with suppressing some of this fluctuation. But in the oxide system, like reason that you might be able to realize higher temperature superconductivity is because the interaction scale is much larger, right? Because the molar system, by introducing the twist, the interaction actually is become weaker. So if you want to, it's a balance of how to tune those interaction energies, and so it's a complex, I would say, phase space that one can explore, and potentially I think this is some of the things that quantum simulation is good at, right? So it's like to maybe explore some of these large phase space.
Yeah, thank you. If I can relate to this, what do you mean here? Is it really superconductivity of charges, or is it superfluidity of the exciton?
Is the prediction is made for superconductive charge, but people have already predicted superfluidity of exciton. Okay. And in fact, this is some of the things that we would like to experimentally measure. So as long as the J is comparable to U, then you would be able to get superfluidity. In this particular material system, Rj is many orders of magnitude smaller than U. So it's very strictly in the model regime. But these are some of the ideas that have been discussed with Yi Hang also, just to maybe think about combination that would allow you to look at this phase transition in particular. Yeah.
Very interesting talk. Thanks a lot. I tried to get a feeling for the length scales of these excitons. Is that nanometers? Is that comparable with the corrugation wavelength that you will get? Like corrugation must be a big issue. I think it's 4% that is mismatch, right? Between tungsten selenide and sulfide.
Yeah, so the exciton size themselves is about a few nanometers or on that order. The quantum dots, they would be probably larger because the exciton binding energy is smaller. So they probably more be like, maybe 6-7 nanometers. The propagation length, is that the second part of the question?
The corrugation length, right? I mean, when you put
propagation. Yes, I mean, yeah. You would have to overcome that, the spatial heterogeneity or spatial disorder. If you want to look at any of these quantum effects, basically you want the spatial disorder or energetic disorder to be the smallest number on here. So it has to be smaller than J if you want to look at a quantum effect.
So you need it as flat as possible.
Yeah, so again, you should talk to Yi Hang, he's the expert. and this is partly, I think it is partly a materials challenge. And so the question is if you want to really have industrial scale application of 2D material, this would be a problem that people have to address. Right now, we all use this explorated method to get as perfect sample as possible, but they are micron scale, right? So yeah, for sure, that would be a big challenge.
Very impressive talk, Libai, but as some of us know, in photosynthesis, this is how we harvest the sunlight.
Mm-hmm.
Yeah, so we have those antenna pigments.
Yeah.
And I have a few questions in relation to that, because basically we do the light harvesting by the same exciton migration, and there's photosynthetic complexes. So first of all, have you thought of going from these nanoparticles to a single molecule, fix them the position, maybe that reduces your heterogeneity, because the light harvesting proteins, they have those chlorophylls exactly positioned and fixed. And then also, I think some photosynthetic systems can keep that to microseconds because of the environment engineering. So I'm wondering if you had any thoughts in that direction.
Yes, in fact, it is a great question, Yue, thank you. And photosynthesis is actually kind of a beautiful system if you think about how optimized that system is, and including some of these. The last part I talked about a quantum dot, where you balance the energetic disorder and dephasing. The photosynthetic system has done that to some extent. This optimal transport regime actually happens around room temperature for photosynthesis. And so we have been, as part of the center, we have been thinking about a lot of questions about how do we couple multiple molecules together, and perhaps not using protein, but using nanophotonics. So you can imagine if you have a photonic crystal, you can put this molecule at certain location with photonic crystal and to look at how they interact, and to, for example, perhaps can learn from protein on how to overcome dephasing and decoherence. And this is kind of some of the things that photosynthesis is particularly good at, and including, in photosynthesis, there's some leading theory on how the wide-barionic coherence might play a role. And so in analog to this, we'll be looking at coupling between the electronic degrees of freedom with the vibrational degrees of freedom. And so that's vast space to be explored in that regard, yes.
One last question, yes.
Regarding the Bose-Hubbard model of your experimental setup, I'm curious how relevant or accessible higher order on-site interactions are.
Yes, so the on-site interaction, in this case, we don't, in this particular materials system, we only can fit 2 exciton in one site. So if you put more than 2, they no longer being confined by the potential. So we have not looked at more than 2 body collision basically. And in this case, the exciton annihilation would be the dominant mechanism that would annihilate one of the particle and you will leave it one only. But we do look at other interaction that is longer range, and potentially you can also look at high order interaction, like for example dipolar or like quadrupolar. Those type of interaction would also be very interesting to explore because that will give you another dimension of controlling the system.
Thank you.
Well, I just want to first of all congratulate Libai for an outstanding award of the proposal and great talk that I'm going to watch on tape later on YouTube. Thank you, Lucy, also for introducing, moderating the Q&A. My sincere apologies because I was supposed to be back well over an hour ago, but the state Senate Budget Committee hearing got delayed in their start. So my presenting Purdue's budget also got delayed. But I'm trying to get as much resources as possible for Purdue colleagues, faculty, and students. We'll see. But sorry to miss the beginning of your talk, and I look forward to be learning a lot from your papers and video recording here. Thank you for coming here. Again, I just want to highlight what a fantastic colleague we have in Libai. In your own scholarship and publications, also in your leading the great group and daring to aim very high and succeeding in winning very competitive large grants. So quantum itself is very important at Purdue across all dimensions, from quantum chemistry and quantum computing, quantum sensing, and quantum photonics. And we have great groups of colleagues, including the one that you put together, working with 7 other institutions. And we, across the board, strongly support quantum as a key part of Purdue Compute's initiative. So again, my apologies, and I'm trying to read as much as possible from all your work, and I've been just blown away by the caliber and the quality of your work and your leadership. Thank you so much.
Thank you, Professor Meng, and yeah, it's a great pleasure. Thank you for the invitation, and thank you for your support for our research as well. Yeah.
I think there was one more question there.
Go ahead.
Based on the comment of on-site loss, if they're coherent and they have on-site loss, you get products of suppression, and that could give you really strong on-site interactions.
Oh, interesting.
Could that
Yeah, we can discuss more. I mean, I think the we sort of like in this initial work that we just did, kind of consider the timescale separation, like because the on-site loss is going to happen at a timescale that is much shorter compared to when we're looking at the quantum phase transition later on. So we haven't looked at those particular aspects, but it'll be it'll be great to chat more. I would love to hear more. Thanks, Lee.
All right. Well, thank you all. And I'm also asked to remind everyone that the next Westwood lecture is April 8th. It'll be Majid Kazim talking about drug discovery from in silico to in vivo and validity. So I think that'll be another very exciting talk for someone from science as well as agriculture. So